For my final project, I tackled the bone marrow biopsy handle, which is currently not ergonomic. To understand the fallbacks of the bone marrow biopsy handle, one needs to understand the bone marrow biopsy process. What is a bone marrow biopsy? It is the removal of a small bone marrow sample, which is a soft tissue in the center of most large bones. The biopsy is conducted if a healthcare provider thinks a patient is having a problem making blood cells, and this sample is sent to the lab to be tested. The sample is typically taken from the pelvic bone, and the patient typically lies on their side or on their back. However, can you imagine the amount of force required to drill through a patient's pelvic bone while keeping the tip of the needle stable and in line? All of the clockwise and counterclockwise motion is uncomfortable and takes a toll on the surgeon's wrist. The procedure goes as follows. The patient receives local anesthesia and the stylet is inserted into the hollow needle. The stylet has a razor-sharp edge. The surgeon grips the handle with one hand and applies force to turn the needle clockwise and counterclockwise further into the patient. Once the needle reaches the cortical bone, the cap is unscrewed, and the stylet is removed to reveal the hollow needle. The needle is again rotated deeper in a straight line, clockwise and counterclockwise, to carve out a small piece of bone marrow. Extreme care is taken to ensure the needle is pushed straight into the patient, because the marrow can be compromised if twisted at an angle. If this occurs, the surgeon will have to repeat at a new incision point in the pelvic bone. The needle is then rotated 10 times and then pulled out to remove the bone marrow sample. However, can you imagine the amount of force required to drill through a patient's pelvic bone while keeping the tip of the needle stable and in line? All of the clockwise and counterclockwise motion is uncomfortable and takes a toll on the surgeon's wrist. My project goal was to make a more ergonomic biopsy handle, which would decrease the physical toll on surgeons. I also wanted to design a more stable handle, which would decrease the number of unsuccessful sampling attempts. So I went to the drawing board with one main idea, to design the bone marrow handle to be two-handed rather than one-handed. This would allow the surgeon to apply force from both hands, making it easier to drill into the bone. Two hands also add symmetry and stability to keep the tip of the needle in a straight line. I was inspired by the way our hands grip the handlebars of a bike or a car steering wheel, steadily rotating clockwise or counterclockwise. These motions eliminate work from the wrist, thus eliminating potential wrist injuries. However, rather than designing the handle to be circular, like a steering wheel, the device could be gripped similar to a jackhammer, with the closed fists in line with each other. When designing the handle, I made one side of the handle be 3.5 inches, which is the average width of a male hand. For the needle length and diameter, I used average values for bone marrow biopsy needles. I chose my handle to be polypropylene and injection molded as a single-use product. Since excessive force is applied to the handle, I had an iterative design approach. My plan was to 1. Make a design, 2. Conduct finite element analysis, and 3. Make design changes accordingly. Inspired by the cystoscope, my designs have a clamshell for plastic injection molding, which have been drafted appropriately. There are 4 bosses with alignment features for screws to secure the two halves together, as well as a snap fit along the edge of the halves. The handle needle is secured within the two halves, and the stylet fits snugly within the handle needle. There's a half moon cutout in the top of the stylet for when it is eventually removed. There's a cap that screws into the top to hold the stylet in place. There are 2 scenarios that I simulated my designs through. The first is the downwards force perpendicular to the patient. I applied 100 newtons to each handle, totaling 200 newtons, which is close to a bag of rice, which I estimated to be the amount of force needed to drill into bone with a sharp point during this procedure. These are the FEA results on my first design iteration. As you can see, there are significant areas of red, which I will work to eliminate. The minimum safety factor throughout these FEAs is often due to the tip of the needle, which I designed to match that of the Jamshidi needle, although not as sharp, so I chose to focus on eliminating the red on the handle rather than the tip. The second simulation scenario was the rotation force tangent to the patient. I again applied 100 newtons to each handle. I found the results to be not as drastic, illustrating that the downwards force is more significant to address than the rotational force. To address the red areas of my FEA, I increased the width of the handle from 16 millimeters to 20 millimeters. As a result, When I reran the FEA, I had less red area, but there was still red. I noticed there was also a significant amount of red on the cap, so I iterated one last time by making both my design handle and cap taller. These design changes worked, as the third round of FEAs no longer had any red. Adding more material stiffened up the handle. The FEA with the rotational force also has safety factors all higher than 1. I ran the FEA one more time, but with the stylet removed, since the second part of the bone marrow biopsy is conducted without the stylet. These results also had safety factors all above 1. A LBM of my final design with a labor burden rate of $10 per hour totaled $16.25 per device. By designing the handle to be two-handed rather than one-handed, I eliminated wrist movements, allowed the surgeon to apply more force, and added more stability to hopefully harvest more successful bone biopsy samples.